I'm back, and now we want to talk about what do nucleuses do that produces energy. And so there are two different ways of getting energy out of the nucleus. So you're going to have nuclear fission and then nuclear fusion. So you should be able to explain to me the difference between fission and fusion. So with fission, you're going to start with a large nucleus, and then it's going to break apart into two smaller nucleuses, and then also that's going to release energy when that happens. Then you could also have nuclear fusion. So in fusion, you're going to start with two small nucleuses, and you're going to smash them together into a larger nucleus, and then that's going to release energy. All nuclear power plants on Earth as of 2024 use nuclear fission in order to generate energy. And so normally it's like uranium that is undergoing fission, and then that produces heat, energy, that is then used to boil water and make electricity. The sun undergoes nuclear fusion. So in our sun today, it is smashing hydrogens together to make helium, and then that is releasing energy. So be able to tell me the difference between fission and fusion. All right, and then another thing you should know is that iron is kind of halfway between fission and fusion. So the element iron, if it was to undergo fission, so take an iron nucleus and pull it apart, it will not release energy. And then if you take iron and you smash it together and you fuse it, it will not produce any energy. So do you remember the noble gases in the periodic table? So that was like, for example, helium. If you light a match and you stick it to helium, nothing happened. So the noble gases are chemically inert. The iron nucleus is, I hate to use this word, but nuclearly, so that I just made that up, but it's nuclear processes, it's inert. And this is going to have dramatic consequences in stars. So when a star begins to manufacture iron, then there's not going to be any nuclear explosions keeping gravity at bay. And then that star is going to collapse, and it's going to go supernova when that happens. Okay, so be able to explain the difference between nuclear fusion and nuclear fission, and then also realize that iron is kind of halfway between being a large element and then a small element. So it does not undergo nuclear fission or fusion. So I would like for you to be able to do an example of nuclear chemistry. So in nuclear chemistry, all you got to do is add the top numbers together and add the bottom numbers together, and remember that the arrow is like an equal sign. So in this example here, hydrogen is being smashed into helium, and we want to know what does it turn into. So you're going to take the 2 plus the 2 makes the 4, and then the 1 plus the 2 makes the 3. And then you can use the 3, the atomic number, to determine what element it is, because it's the atomic number that never changes. And then the one underneath it is an example of nuclear fission, but this time you have to subtract in order to find out what the missing element is. So here is what it's going to look like on the exam. You have to fill in the question marks. And so here's an example of a nuclear fission problem. So, when the nucleus undergoes either nuclear fission or fusion, what's going on? How does it release energy? Well, it has to do with the binding energy. So the binding energy is the amount of energy it's taking to hold that nucleus together. So when you're either smashing things together or you're pulling things apart, it's that binding energy that's being released in the reaction. So how does it come out? How is this energy represented? It's represented by missing mass. So you have the nuclear material before the nuclear reaction, and you could weigh it, so it has a certain mass. Then after the nuclear reaction, you go around and you pick up all of the debris, and you take the debris and you put it on a scale, and it's going to weigh less. That missing mass is what's going to go into this formula. So this formula is Einstein's famous equation, E equals mc squared, where m is the missing mass and then c is the speed of light. But remember, you got to square it, and then that would be the energy released in joules. So here is an example of how to use the formula. You should be able to put numbers into that formula and actually calculate the energy released. All right, let's take a break. And when we come back, we're going to talk about radioactivity.